check our streaming settings, make sure that we're actually up and running. So let's see, coming in here. And it says we are live. Check our streaming settings, make sure that we're actually up and running. So let's see, coming in. I'm just checking to see, is my computer slow? It looks like we're good. I can hear sound, and the video seems like it's working. Cool. All right, we're up, we're running. I won't have chat on. I'll come check on the chat later, but okay. Coming back to looking at these kinematic constraints. In the last video, I went through kind of the background of how to describe moving bodies. And in this case, we were looking at a top-down view of a door, so a door moving in one plane. And really, its motion is all two-dimensional. Like, there's some hinge here at this point, some point here, and then its center of mass is rotating around that hinge. There's a handle. So what I wanted to do today was actually look at like why go through this and how does that actually help us define like multi-body dynamic simulations. And a lot of dynamics ends up just being kinematic problems where you're just looking at like what are the constraints on the motion, how do I set that up, how do I define these constraints. So I have the moving door frame over here. It has these different coordinates, like its position, so x1, y1, and then theta 1 over here. So let's define those in our Julia notebook. So what I wanted to do was I need symbolic definitions. I'll zoom in. All functions of time. And I'm doing this so you can kind of see like how. So we're gonna say using symbolics, and I'm gonna say also plots, and I don't know what else we'll need. Oh, what's wrong? Oh, duh. Using, there we go. So at variables, let's zoom in some, t for time, and let's wrap this in a begin, and then at variable x1 and I think there's a, there we go, theta sub 1 of t. And then LaTeXify. let's see if that one runs. And I think I thought that it would make an underscore. Let's see if I can change that. No, that's okay. I like it if it's a subscript one, but that's okay. Okay, so I've got my variables defined, and that's defining just my door here. Now I want to start defining what my constraints are. So I'm going to say that I have constraints that are Q and T. So I have constraint equations that are Q and T. And let's start with another begin and another end. Bump that one over. That means I need to define what Q is. In this case, it's just my X, Y, and theta coordinates of my door. So let's do that. Q is X1, Y1, theta 1. And now I can start defining what these constraints are on my system. So let's come down to what we're working on down here. That one's our Jacobian. Here we go. So here's my constraints, where I've got Q of 1 minus we'll start with this, W over 2. Oh, and I want to transform it, right? There we go. Minus W over 2 times cosine of Q3 minus T over 2 times sine of Q3. And that's just my first constraint. My second constraint is that Q2 minus W over 2 times sine of Q3 plus T over 2 times sine of times the cosine of Q3 is all equal to 0. Then the last constraint is something where I want to define that there's motion happening, and the one that I had come up with was saying that the center of the door was moving, and we can keep that. Why don't we keep this one? That I think a better way of doing this would be saying that the door handle, and I know I'm scrolling up and down, it's hard to keep track. Better way would be saying like this door handle is going to move at a certain speed, but we could say like we open the door handle, now we're pushing on the center of the door at a certain rate. So let's stick to that the center is going to open at 2 meters per second. So our last constraint is that Q of 2 minus 2 times T is equal to 0. Like this. And so far, this doesn't seem like we've really done anything, but this is actually a really important way of defining systems of equations this way. So I have 3 equations with 3 unknowns in this case. I won't always have 3 equations, 3 unknowns, but if we have a purely kinematic, like 0 degree of freedom, or at least Grubler count is 0, in this case it is 0 degrees of freedom because all my motion is constrained somehow. Then I end up with, oh, and should I put this down here? Because I could put this, I could move this stuff up. I'll mess around with the, I was just on a roll as I was thinking about it. So if I give a Q that has the right X, Y, and theta, then this answer should say that I should get a set of 3 zeros out of that. And at first, so we get a generic function. I think it's going to give me an error if I try to use it. So let's tell it that we have a 0, a 0, and a pi over 4. This one should be wrong because we had set up a constraint that these can't be 0, that they can't. And what did I say? Oh, the mx and my of the door, of the door frame. Because right now I'm saying that the hinge is at 0. So let's subtract an mx and an my to say that there's some non-zero place where the door frame is. And what I should get is an error, is that there's some stuff that's not defined yet. And it's thinking about it, probably gonna spit out an error. Yeah, W is not defined, and that makes sense. So let's start defining our, so we have width and thickness. I think width of the door, usually doors are like 2.5 to 3 feet, so I can call it 1 meter. It's kind of a large door. That's not bad. No, that should be fine. Let's call it 1 meter. Thickness of the door, usually just 1.5 inches or something. So 0. We'll call it 2.5. We'll call it 3 centimeters times 10 to the negative 2. And then the hinge we'll say is, let's see, we'll put mx as 0. So just putting this location as 0. But we'll put the my equals the thickness of the door. So the bottom of the door should lay along the x-axis when the door is closed. That's what I'm thinking for this one. So now let's try this. Oh, whoops. I can't have these two because I have time and thickness. So let's call this capital T. And this one I'm going to call capital W. One thing I do like about these Pluto notebooks, it's both annoying and helpful. But the helpful part is that when I set up my variable as time, if I use the value of t again, I can't use it twice, so it warns me. It gives me an error because it's like, hey, look, which value of t are you trying to use here? Okay, cool. Now when I try to run these constraint equations, I get this thing of telling me like, hey, look, you do have a 0 over here because we happen to say 0 minus 0 is true. And actually we should say that at time 0 the door is closed. So Q2 shouldn't be 0 at time 0. Q2 should be thickness over 2. So minus t over 2. I think that would work. So now, even though the door... Yeah, so door is like trying to be 45 degrees, but none of my constraints are being solved. Okay, so now the cool thing about this is that when you're using computational methods, like for here we're in Julia using Pluto, once you define a function that can be 0, that if it's 0 then you have the right answer, there's tons of methods to figure out how to find the right answer. So let's grab this. We're going to copy it over, and let's just make a new one so it's not... I need you to... no. I need a root finding function in Julia to solve this set of equations for my multi-body dynamic problem. So now it should be looking for and this is exactly what we're trying to do, is figure out, really it should be 0, 0, 0. So NL solve nonlinear constraint function. I already defined the constraint function, so I don't want to do that. I just want to solve it. Let's see. I'm trying to find where this thing... So it's creating a solve constraints. But I just want to grab a solver, a root finding solver. Use a built-in root finding solver to solve C Q given T in the C of Q comma T. Because what I should be able to do is just tell it, okay, here's time 0, solve for the values of Q that give me all zeros. Yeah, nonlinear solve. I don't know why it's defining this again, because I already defined it. I just want to solve it. So a nonlinear constraint residual, initial state Q, and parameter tuple. Let's go look at nonlinear problem. Non-linear solve as NLS. So in this case, what it's doing is create two steps, a nonlinear problem and then solve that problem. We can do that. PROB is NLS dot non-linear problem of C. U0, we can give it 0, 0, 0. I don't think it'll give us too many problems. I don't think I need a lower and upper bound. Let's see if that's not required. Prob and Newton-Raphson. I don't know how it's going to do a Newton-Raphson if I'm not. Oh, P. Wait, what are P? Oh, the parameters. Give it a shot. Let's wrap. So this is differential. Yeah, I guess we do have differential equations, right? One-sided bound, in-place formulation. So I think we need differential algebraic equations. I think that's what this one's saying. Differential equations in algebraic. Differential equation algorithm. DAE. No? Not letting me find it. General keyword arguments. Sorry, I'm jumping around here to figure out what I need to do to get this to give me the thing that I am looking for. Let's try this. C0 equals C of Q equals C of Q and 0. So it's giving me an error here saying there's some kind of problem with the SciML. But I'm not trying to use an ODE solver. I wonder if it's giving me a problem because all of these Q values are so I was trying to create this Q in terms of variables here, but I wonder if that's giving me a problem because now I don't have numerical things. I actually have like symbolic representation. So let's try this. See if this one helps. This will help us if we have symbolic so that we can do Jacobian work on it, but it might be causing problems down here. Alright, let's dump this into getting an error in this code. Oh, no, don't run, don't run. And then we'll grab this guy. Oh, and I wonder if the fact that I have like time set up because right now time is also like an actual symbolic value. I don't want to send this in because that's Not a syntax error. Oh, because I'm creating that ODE problem, which I think yeah, I might want to use like time this way. Because t here is a variable. All right, we'll try that out. This one should be so I'm not trying to solve an ODE, right? Let's comment out this stuff. Because right now I'm not using that. Let's see if this one works. It's going to tell me to wrap it beginning end. Oh my god. SOL and prob. Nonlinear problem is not defined. So I have to say NLS dot. And then I think I want to say NLS dot. See, I'm still getting this thing where it thinks it's a differential equation. But I don't really have like a differential equation. These are just the algebraic equations. Technically we have a differential equation because I'm saying that there's something that's a function of time. So this one didn't help at all. So I'm going to delete it. I don't like it. See, I like the way that I set it up like this. But it's giving me that same error. Let's see what the error is actually telling me. So this one's setting up an actual differential equation and solving for the ODE problem, the differential versus an update where it's updating so two different ways of entering functions here, both of them using nonlinear solve, using I guess I could try that. And then I shouldn't have to say MLS dot. And it's telling me to try this command and see what I get. Importing non-linear solve. Yeah, this is still getting hung up on this differential equation, and we'll figure this out, because the main thing is just, look, I have three equations, three unknowns, solve for those equations. I mean, I could use a parameter, right? But I don't want the psi-ml. recognize keyword. I'm just trying to give it a parameter, right? Because this is showing me that I can give it. No, I'm trying to do this one, nonlinear solve. See, in here I've got parameters f u0 comma p. What if I just tell it to solve it? I don't care how you solve it, just do it. Geez, that wasn't so hard, was it? Okay, so what am I doing here? I got an answer. Let's see if the answer actually makes sense. What I am starting off with is I'm giving it an initial guess of 0, 0, 0. It's not a good initial guess. I know that it's going to be wrong, but it's going to be pretty close to what it should be. And then it's telling me that my initial X position is half of the door width. My initial Y position is half of the thickness. And then my initial angle is 0. And then if I change this and say go up to 1 second, now it's updating those answers and telling me like, hey, you're over here on the negative, like the door is swinging past the x0, past like the 0 position, or about 0, 10 to the negative 9. It's a nanometer past our, if we look in here, a nanometer past this origin, and the door has reached like 1.3, and the angle is 1.6 radians. All these functions are gonna, any angle that we're talking about is always gonna be radians. We can convert it to angles afterwards, but math is always done in radians. Okay, cool. So we've got that. Now we've got a way of solving that nonlinear problem for any time. So 0.1 seconds, we can figure out, okay, 0.5, 0.2, 0.4. Those are my generalized coordinates for Q1, Q2, and Q3. This is easier than I was making it out to be. I was trying to be kind of fancy and use like symbolics and all this cool stuff, but we'll start simple, right? Get something that works, and then we can always optimize it later. So that's, and then this parameter P, I just use that as my placeholder for time. The P is time there. Cool. That's what I wanted. Now, so I know where, I can figure out where everything is. The next step is how fast is everything moving. Since I said this, I said that the center of the door has to move at 2 meters per second. So how fast is everything else moving? Is it constant? Is it, and actually, you know what? Let's do this. We'll say capital Q, like all my general, I don't like that. So Q all is gonna be zeros of and we'll call this one time is gonna go from, I always forget, I think it's Lagrange. Let's go from 0 to 1 second. And let's look at live docs. 0, 1. So I think I can say 0, 1, and then give it the number of steps that I want to take. Let's go 51 steps. And now I want this one to be zeros of 1, gives me 1. And then 2 comma 3 would give me like a 2 by 3. So let's say length of time, comma 3. What I'm doing is solving for all the values. I want to say row I, and all the values are SOL. And let's see if that one worked. And I should give it an end. Oh, this should be a time bracket I. I don't know why I gave it a... Let's just plot time and Q all. See if I can get all 3 values up there. Now the question is, does this make sense? Let's think about it for a second. So Y1, that's my Q1 value. That one is my X position. So Y2 is my Y position. So this is really describing. So it starts off here. It's supposed to increase at a constant rate, but then at some point it changes and it's not increasing at a constant rate. Meanwhile, my X position goes from 1/2, which is half the door width, swing, it keeps decreasing until it hits basically 0 and then stays 0. And then my angle, here's this Y3, angle's increasing and then hits some constant value. So is this really true? Like, is this what's happening? And what I think that's really happening here, at least from looking at this plot, is that I'm creating a constraint that can't be followed, where I can't keep increasing the distance of the center of the door. Like, the max distance that this can really get to is 1/2 of the door length, which is right about here. Like, it can only go this far. So really I can only open the door for 1/4 of a second. That's what I'm seeing with this plot. So maybe 0.27 seconds or something by time I get to that max position. So let's try that, 0.27. And still too big, 0.25. And sure enough, now we have a constant Y2 opening, so the velocity of Y2 is constant. and y3 is our angle. So it starts off relatively constant speed and then starts increasing towards the end. And our x position, so the door, how far it swings to the left. Like it starts maximum distance and then keeps getting smaller and smaller. All right, so now this seems a little better to me. It seems like we're satisfying these equations, and we can even check, right? We can say C of Q all, and let's go, we made like 51 time steps, so we'll say 49, and time of 49 why doesn't it like that? Oh yeah, comma, colon, there we go. And here I get three values, 10 to the negative 6, 10 to the negative 17. If you're not used to using computers, this is a 0. Like when you're doing math on a computer, anything less than 10 to the negative 16 is a 0. And when we get up to 50, now we start seeing that it's not quite 0, like something's weird about the angle, 0.01. When we get to 51, oh, that's why. I didn't change the time. Yeah, so it's still 0, even as we're getting out to that max time, versus if we try this out to 0.5, now we can see something's weird. And if I look at the last value here, these, although my x position is around 0, so somehow I'm satisfying that constraint. And really that's because if I just keep pushing the door further and further open this way, like y just keeps increasing, really I'm just saying that x is going to be here. It's just going to reach some constant value and it's not going to move anymore. So that's why I can satisfy that one, but my y position and my theta position are not working correctly. So it seems like 0.25 seems to work. Let's see, y minus 2 over 4. So y minus 1/2 minus that t over 2. So we could probably go slightly more, but this is fine. This is pretty good. Okay, so what I just did here, kind of recapping, is set up my constraint equations. So 3 equations, 3 unknowns. If we have more degrees of freedom, if we have more generalized coordinates, then we would also need equations of motion to describe like what are the forces on this thing and how does that affect the accelerations. And so because I had 3 equations, 3 unknowns, that means that I can solve for any point in time, I can solve for what these are. Usually they're nonlinear, especially with things like hinges here, rolling constraints, all that stuff ends up being like nonlinear equations because of these sines and cosines. So I do need some kind of nonlinear problem solver, and that's why we went through the trouble of solving it with that nonlinear, like creating this thing called nonlinear problem and then solving that problem. Next, we can do the easier part, which is, well, I don't know how easy it's going to be. I'm about to try it. Is create the linear algebra problem to figure out how fast is everything moving. We have numbers here, so technically we could take derivatives since we have positions at every point in time. But I have very specific constraints on position already. I can take a derivative of that, which I did last time, here, and then solve for those values of Vx, Vy, and theta dot all right here. So let's try that next. So I'm gonna say dc dq is a 1, a 0, and that a theta times negative w over 2 and t over 2. I'm just trying to remember. So I need so it'll be a cosine theta negative oh yeah, and this is a function of q and the parameter, because I'm taking that derivative, it doesn't take away the time constraint. Here kind of does, like the time, it's not a function of time anymore because we had that linear portion of time. But we'll leave it like that. Negative w over 2 times cosine theta, and then negative, I'm just trying to get back to my that should be that is silly. So it should be a negative sine of q3, because this is my a theta term over here, and then a negative t over 2 times cosine q3. And I always forget how to make, just a comma. And then a 0, a 1. And now we've got a w over 2 times cosine of q3 minus t over 2. And should that be a negative? I think it's a net, because I have a negative w over 2 and a positive t over 2. So but before it was a negative times a negative, now it's negative times positive. And then a negative times that sine of q3. Looking good so far. And then the last row is a 0, a 1, and a 0. Just like that. CT of Q and T, Q and parameter, is a 0, a 0, and a 2. And let's just try. Doesn't like that. Unexpected comma in the array. Let's double check. Make a new one. Oh. getting an unexpected comma in this array definition. Let's see if that one works. There we go. Semicolons for rows. Oh, so a semicolon and then a space. Okay, I'll try that. Alright, so I was just double checking that, and so this is giving me integers. It shouldn't really matter, but really I'd rather have float numbers for everything. Personal preference for this one, I think it would probably not matter, but if I'm doing everything in terms of floating point numbers, I just don't see a reason to define a vector in terms of integers that's going to get converted to floating point numbers, even though this one's always going to be 0, 0, 2. Could just be me, but all right, so now I can do the same thing that I did up here, where I can figure out what the let's do this. We'll copy this whole for loop. And instead of creating a nonlinear problem, I'm not going to do that. I'm going to define, and yeah, it might complain that its solution is defined twice, but we'll see how it goes. dc dq of q comma time of I, and here, although theta is changing, there's no actual like time dependence in this case. Hinges and prismatic constraints don't have a time dependent thing. They do depend on the actual variables, so x, y, and theta, but there's no direct time dependence. And then we want q all bracket I and time I backslash ct of q all bracket I and time I. And I'm creating dq all because I'm going to solve for all the derivatives of each of my each of my generalized coordinates. And now, instead of creating like a nonlinear solution, I'm just creating a linear solution to this. At index 3, what's your problem there? Oh yeah, this one. Let's call it QT is so Q at time t is Q all I comma colon. I think it's just figuring that out. Oh, and it didn't complain because the solution is inside this SOL that I'm redefining is inside my for loop, so it seems to be okay. So now let's try this. Plot time and DQ all. Look at that. We have a constant value for y2, which is exactly the constraint that we wanted. It's 2 meters per second the entire time, versus y1 starts off near 0, because if you think about the limit for a small cosine term, which is our x position, it should be constant for a little bit, and then as the angle gets bigger, now it starts moving faster, and then versus our angle here the theta starts off kind of moving slowly and then ramps up towards the end. The more the door opens, the faster that angle has to open to keep up. Okay, so now what I would like to do is I need you to give me a Julia function that plots a rectangle given its x, y position and orientation theta in a vector q equals x, y theta and let me define its width and thickness for the plot. Let's see if this one gives us what we're looking for. So what I want to do here is show like the door actually opening in real time. So I have plots. Let's see if this one works. Theta is in radians. So plot oriented vector, rectangle, and then do this. Let's see if this actually does what it says it's going to do. Wrap in a beginning and end, and oh, look at that. Base plot is this plot oriented rectangle. Let's see, rectangle width, rectangle thickness. So I want a 1 meter rectangle. Well, let's just call it our width and thickness, like that. And we don't need that big of a zoom in a little bit. And we don't need this to be a -1, let's say a -0.2. Okay, so now I've got this. Great. Also show a vector for its show an arrow for its velocity vector Vx, Vy at its center. I wonder if this will work. I think this is making it more complicated. All right, so next, really, I just want to do an @GIF thing. So Julia plot @GIF, so I can watch it open. Animations. GIF for I in 1 to length of time. We're going to say Q all of I is our pose, and then we can end it. What's wrong? Unexpected end. I guess we didn't need the beginning and the end here. Why didn't this thing like it? Oh, my AI doesn't seem to work. Alright, AI has been. I'm getting an unexpected. Oh, here. I don't need that, do I? Look at that. Zoink. Opening door. And look, the hinge. If we kind of zoom in. Can I zoom in? Not really. But the hinge is not there at the center of the door. It's right there at the corner as it's kind of opening up. Pretty cool. And some other cool things that we could do is like add the velocity, like the velocity vector here. Of like we would have a constant vertical component and then a growing leftward component. Cool. Edge color black, orange, magenta. There we go. Pink door. So anyway, long story short is we went through the process of taking our hard work of defining multibody dynamics. And the great part here is that we've defined the solution that we've made for this hinge is a general solution. If I want to change the location of this hinge, I can do that pretty easily now, and I don't have to change what my coordinate systems are. So let's try this. Let's put the hinge at 0.1, so we'll move it 10 centimeters, and then we're gonna put this thing at 0.20 centimeters. So we're gonna change the location of the door. It changes all of our X and Y positions because we changed where the door is, and these are giving us like global positions. The velocities for the most part should stay kind of the same, and and the doors, yeah, we're giving it a different range of motion for the door because we moved this thing up, but we left our constraint that the bottom of the door had to be down here at like 0, at time 0, which is also kind of cool. But we could change that too. We could change what those constraints are. Up here in this part, we could change what that initial offset is. But there's lots of possibilities now because we're starting to look at things in a general, like, global sense. And doing this in 3 dimensions adds some complication, but really it's just there's more bookkeeping. Here we were just keeping track of those 3 coordinates for one moving part. If we were looking at 3 dimensions, then we would have 6 coordinates. We would have an X, Y, Z position and 3 sets of angles to keep track of. But hopefully this was fun. I thought it was cool, and we end up with a cool animation of this thing. Let's set this up. Let's go out to 1.5. Yeah. There we go. So now it's opening, and we'll get this down to like -0.5 so we can watch this door swing open that way. And we're pushing on that halfway point. Whoop, right up there. Cool. All right. Thanks a lot. Thanks for coming on this journey through some Julia work, through some AI integration, and I will see you next time. Have a great day.